Okay, so a couple reminders. I sent an email saying there's a field trip this Wednesday, completely optional, has nothing to do with the grade. Just think if you are interested in going and seeing a real data center, sign up for it. Even if you're not, you can go to the poll page and mark a no, so at least I know that you have responded one way or another. Okay, so use that today because I need to finalize the count, head count of how many people are going and let them know. Okay. All right. So we just continue some of the last couple of topics here. So today we'll do a discussion of distributed security, and next Wednesday, which is this 2 days from now, we'll just do a course wrap up and the last case study on middleware. Okay, so just 2 topics remaining. Overall, we've done okay on time. So today's discussion is going to be on security. It's somewhat abbreviated discussion than what we used to have a few years ago. This is because there is a graduate level course on security now. So if you want to know more about the topic, that's the course to take. Here I'm going to only give a quick introduction to security topics and explain why this is important in distributed systems, somewhat like what we did for fault tolerance. Okay. So the first part of the lecture is going to be on very basic security mechanisms. Some of you may already know about the basics of encryption, decryption and things like this. So I'm not going to dwell too much on that, but I'll go through that material quickly. And then we'll talk a little bit about how security is implemented in network systems, distributed systems, how you can use some of these principles to build interesting use cases. Okay, so that's really where we are going. So the figures here essentially show why this is important in this context. We have a distributed system. Essentially, a definition allows any machine or a network to access data and or computation. So, and as well as users. So some of the users could be malicious. We want to prevent our system from malicious parties. Okay. This could include not just hackers, which may be actually trying to do bad things to the system, but also more straightforward things like unauthorized control or access control. Okay. There may be some data that only certain people in an organization are authorized to see. If this is not protected appropriately, it may be inadvertently visible to others who are not supposed to see it. As simple as that. So what are things we need to do to prevent against invalid operation, unauthorized invocation, users and so on. So that's really the gist of where we are going. I'm going to start with the first problem that you would like to address, which is authentication. Authentication is the problem of proving to a system that you are who you claim to be. Okay? So before you access any resource, you need to authenticate. You need to say, I am such and such. Okay? And you need to be able to prove to the system, and the system needs to be able to verify. The second part is, then you say, I want to perform, having told you this, I want to perform a certain operation, and then the system can check whether you have the right to do so or not. Okay, so first problem is authentication, and then we'll come to the rest. Okay, so basically, you can just go and tell the system that I am such and such. Okay? By itself, that is meaningless because anybody can claim to be you. Right? So you need something better than just say announcing yourself to the system. Okay, so we'll look at some authentication protocol. Okay, the first protocol is what I just said. In security world, you always have these 2 parties, Alice and Bob, that are trying to implement a certain protocol. Here they are trying to implement authentication protocol. Alice and Bob could be people, machine, some combination. Alice could be a person, Bob could be a machine. It doesn't matter from your perspective of the discussion. Right? So Alice can just send a message to Bob saying, I'm Alice. Okay, this is a person just entering their username into the system. System could be Bob, a person could be Alice. Okay? Just by announcing a username, you cannot actually prove to the system that you are who you claim to be. Okay? The reason is the intruder can also announce your username. It doesn't make sense. Okay, another way to authenticate yourself is to actually look at the machine IP address where the request comes from and see if you can use the machine IP address to authenticate whoever it is. Okay? There are many systems that actually use IP address authentication. Okay, so basically they say only messages from these machines will be treated as valid messages. Okay? So it's not as trivial as it sounds. There are systems that are configured to do that. Okay, the problem is that it's very easy to do what is called IP spoofing. Okay, you can actually download a simple Python library and generate any packet with any source address you want and inject it into the network. Okay? And when that packet actually reaches the other end, the source address will actually be misrepresented. It's not the machine it came from. It is whatever you choose to stick into the packet header. Okay? So IP spoofing, which is sending packets with a false source address, is very easy to do. Okay? So many systems that simply use IP addresses to authenticate whether the system is allowed to access or is the right one is really not going to cut it either. Okay. So typically what you see in most authentication protocols is to use a secret password. Okay. So you have a username and a password. This is how you may log into a system, whether it's local or remote. Okay. For one problem that you see in older protocols like Telnet or FTP is that username passwords were actually sent in clear text. So you basically connect to a system. It gives you the username prompt. You specify your username. It prompts you for the password. You type your password. All of those packets were actually going unencrypted over a network. What that means is if any adversary actually captures that packet as it traverses through the network, your username and password are actually in plain text. If you just look inside the packet content, your username is there and as your password. So now you are basically have an unsecure protocol where any password that's going in transit is actually being captured, and now someone else can use your username and password to log into a system. Okay. More modern versions of protocols like SSH obviously don't do that. They encrypt your information before they send. But if the information, sensitive information like username, password goes unencrypted, that's a problem. Okay. There are many protocols that actually do that. Okay. Telnet, FTP, if you don't run many of the web service protocols, like you can actually have a web form, it's over HTTP, where you are asked to log in and you specify your username and password and you hit submit. If the web form is not going over HTTPS, it's just plain HTTP, you just sent your username and password unencrypted. Okay, because it's just going to go as a text message over the network. Any adversary which can actually look at the packet can figure out your username and password. Okay, so there are many unsecure protocols, even though your password may be only known to you and the system. If you send your password in a clear channel, then that's a problem. Okay. So the solution, of course, to the problem is to use encryption. Okay. So you want to encrypt some of the contents of what you're sending or have a more secure protocol to do authentication. Okay. So we'll see many variants of authentication protocol. This one uses basically a secret key that is known to both Alice and Bob. We'll use a key that we are going to use to encrypt whatever messages we are going to send back and forth. Okay, the key is assumed to be known to both parties. Okay, how the key gets known, we are going to come to later. For now, let's assume that there is a shared key. Okay. So in this case, what the protocol is very straightforward. Alice sends a message to Bob saying, "I am Alice," but that message is encrypted with the secret key. Okay, so this is an encrypted form of the message. Okay, Bob is basically going to use the key to decrypt. The same key is a symmetric key. So you use the same key to do encryption and decryption. Okay, so you can extract, you can decrypt the message. So this messenger has encrypted, you can decrypt it and you will get the string saying I'm Alice. Okay. So Bob basically gets a string saying I'm Alice. If the key is only known to Alice and Bob, Bob is at this point going to be convinced that only Alice could have sent that encrypted message. Nobody else can generate that message because the key is only known to Alice. That's at least the idea behind the protocol. So just sending an encrypted message and encrypting it with the key that only Alice and Bob know is basically a way to do authentication. Okay. Now this works well except for one problem. Okay. And the problem is if some adversary actually intercepts this message as it goes over the network, you have an encrypted packet that says I am Alice. that adversary can present that packet to Bob at a later time, okay, doing what's called a replay attack. You're replaying a past message. And when Bob is going to get the same packet at a later point in time saying, I'm Alice, and Bob decrypts that and say, this key is only known to Alice, so it must be Alice who sent the packet. And then you have let an adversary into the system. Okay, so this is referred to as a replay attack. Okay, so just because you have a shared key that you have shared between two parties, only those two parties know it, and you're sending a message encrypted, even that is not going to be enough to guarantee authentication if you are vulnerable to a replay attack, which you will be, because when you send a packet or a network, there's no guarantee what happens to the packet. Anyone can intercept that packet and do whatever they want with it. Okay. Here you don't need to decrypt the message. You just represent the same packet, which is pure, completely encrypted, back to Bob. If Rudy, who is an intruder, does it, then you're going to be stuck. Okay. So then the question is, what should we do to this protocol? So the protocol takes us halfway there. So what can we do to this protocol to make it more secure, to prevent replay attacks from happening? Okay, so that's really the question. Any thoughts?
Some timeout.
Yeah, you can use a timeout.
Add a random number to the message.
Okay, so you can add a random number to the message. Okay, so basically what you want to do is you want to be able to ensure that any packet that is sent now can never be resent in the same way. Okay, so essentially you want an intruder, even if the intruder captures this packet, okay, it should be useless to the intruder for a second attempt to authenticate to the system. Okay, so how do you do this? So it's sort of, you want the message to time out after the first time it is sent. Okay, the way you do this is you basically use what is called a nonce. Okay? Nonce is a randomly generated once in a lifetime integer. So basically it says generate a random number, but generate a random integer such that over the lifetime of this application you should never generate it again. So you generate it only once. Okay, so pick a very large space, okay, 1 to a very large number. From that number, pick a number that you are going, that's randomly chosen, but pick it in a such a way that the next time you call the same library to pick another number, you will never pick it again. Okay, so this is referred to as a nonce. Okay, and the protocol is as follows. Okay, how do you use the nonce? Alice sends a message to Bob saying, I'm Alice, unencrypted. Okay, Bob is basically going to generate a once in a lifetime nonce. Okay, this is referred to as a challenge. Okay, and send. So here is an integer. Okay, now prove to me that you are Alice. Okay, what Alice will do is she will take that once in a lifetime integer and encrypt it with the shared key. Okay, that's only known to Alice and Bob, and she encrypts it and sends that message back saying, here I have encrypted it with the shared key, and Bob is going to then decrypt the message, okay, because Bob also has the key. And if the message, basically the decrypted form of the message is the original integer that Bob sent, you are now authenticated Alice. Okay? Because only Alice and Bob have the shared key. Okay? And you basically generated a one-time random nonce, you sent it over, and Alice could decrypt it with the key that only she is supposed to know, or rather encrypt it with the key that only she is supposed to know, and sent it back. So now you know that only Alice could have done this. In this protocol, it doesn't matter if the intruder actually goes and intercepts this message. It's an encrypted version of a nonce. This nonce will never be generated again. So if an intruder comes and says, I'm Alice, I want to log in, okay, you will generate a new nonce at that point, and the intruder will have to encrypt that nonce, not this one. Okay? This is also referred to as a one-time password. Okay? This is a password you are going to present to the system that you will never use again. You sort of use it once to log into a system or authenticate yourself, and then it's never used. Okay? So just intercepting your password is not going to help because it's a one-time thing. Okay? You will never use it again, so you cannot use it to log in. Okay? Questions on this? Okay, so the main idea here is to use this notion of a nonce. Okay, this is a one-time, once in a lifetime random number that you generate. Okay, notice that I did not actually discuss how you generate a nonce. Okay, there are libraries to do that, and clearly that library has to be well designed. Okay, you have to understand what the lifetime of the application means. Is it 1 year, 10 years? We have to basically make sure that, and you have to know how many nonces will be generated. So you have to pick a sort of integer space that's large enough so that you will never actually have to repeat a nonce. Okay? If you say I have nonces are going to be generated between 1 and 10,000, you cannot have more than 10,000 login entries. After that, you're forced to reuse it. Right? So you better pick that value of the maximum n very carefully, and also have this. So that part I have not discussed how to do, but you will have to actually come up with a good technique to do it. Otherwise, you won't be secure. Yes.
Also, wouldn't your nonce generation have to be centralized? So in a distributed system, you wouldn't be able to have multiple login servers.
Right. So in this case, we are just talking about Alice and Bob. Okay. There are no other parties. There's an intruder sitting in between. Okay. So you don't actually need to have centralized nonce generation in some sense, because this protocol just says Alice and Bob. If there are many machines, you would also probably add the IP address of the machine as well. Right? So it is only two-party communication, saying I want to log into this machine. Okay, so that machine and the nonce is basically what you will use in this case. In this case, the machine name is irrelevant to us because there are only two parties. Yes, any other, but that's a good point. Right? So if you have many entities, they don't need to actually centralize the nonce generation. You can actually add a party-specific information to discriminate between different machines. Okay, so that's one approach. Another approach is what is referred to as using public keys. So public key cryptography is a very popular way to do variety of encryption techniques. Okay, so what I was talking about until now, where you have a single key, is referred to as symmetric key encryption. Okay? There is one key, that same key is used for encryption and decryption, and the key is secret and known only to the two endpoints. Okay? Another way to do encryption, a popular way, is referred to as public key cryptography. You have heard of RSA, okay? Or used RSA, or actually if you use SSH, you probably have used RSA underneath. You have actually public key cryptography being used in this case. The way public key cryptography works is you have basically you generate two keys. Each entity generates two keys referred to as a public key and a private key. Okay? Your private key you are supposed to keep secret. Your public key you can give to whoever you want. Okay? They are also referred to as the encryption key and the decryption key. Okay, so same thing. So it doesn't matter. We'll just use the terms public key and private as the name. So any party that wants to do any encryption will generate a pair of keys. Okay, the key pair is public and private. Public key you make public. You can publish it on your web page. You can give it to whoever you want. Okay? But the way you are actually, and the private key is supposed to be secret, only known to you. Okay? And the way you go about doing encryption is basically very straightforward. Okay, so same protocol again. Alice sends a message to Bob saying, I'm Alice. Bob sends back a nonce. Okay? Alice is going to then use her private key and encrypt the nonce and say, here is the encrypted version. Okay? And Bob is going to take Alice's public key and decrypt it. Okay? And the assumption is that public and private keys can be actually used to encrypt or decrypt. If you use the public key to encrypt a message, the private key decrypts it. If you use the private key to encrypt a message, the public key decrypts. They are inverse functions. Okay? So this is basically, think of this as a function of n that produces a new encrypted message. And if you apply this function, you basically get back. And the same thing, so EA here stands for encryption key, and the decryption key is the same as public and private. Okay, and vice versa. Okay, so they are basically can be used to encrypt and decrypt message. So Bob knows and the assumption is Bob knows Alice's public key because it is public, everyone knows it. So Bob can just get her private key and check whether the nonce is what comes back from the message. If so, you know that only Alice could have encrypted it because only Alice knows her private key. Okay, so you authenticated Alice. Okay. Any questions on this? So this is the property we are going to use, which is you can use the private key to encrypt and the public key decrypts it, or vice versa. Okay, those are sort of inverse functions. You can apply them in either order to encrypt or decrypt messages. So when you do SSH, you're actually you use keys to do SSH, login, not password based. There's typically a public and a private key. You have the private key, you can make the public key, stick that on the account on the server, and when you log in, you're basically using the public and private key to actually send messages back and forth. Yeah, something similar, although nonces may not necessarily be used depending on the system. Okay. So here is a problem that can actually occur with the previous protocol, which is referred to as a man in the middle or a person in the middle attack. Okay. And so here basically what we are trying to sort of do here is see if an intruder can actually impersonate Alice and try to gain access to the system. Okay, so here is what can happen. Okay, intruder Trudy sends a message to Bob claiming to be Alice. Okay. Bob sends a message back to Alice, okay, with a nonce. Okay. But the intruder is sitting in between, intercepting the message, and the Trudy is going to get this message. These are unencrypted messages at this point in time. Okay. So the nonce is just sent unencrypted, so Trudy gets the message. Okay. And Trudy basically is going to send the message back to Bob, saying here is an encrypted version of the nonce. But Trudy only has her private key, not Alice's private key. So this is basically, you can see it's basically Trudy's key, stands with T. So Bob is now going to have to decrypt this. To do this, Bob has to actually get hold of Alice's public key. Okay. Now if Bob actually had Alice's public key, this would be meaningless, because this will not decrypt and get you the nonce because it's encrypted with a different person's key. But the problem arises if Bob actually does not have Alice's key and has to extract it from somewhere. So Bob sends a message saying, okay, I got your encrypted message, now point me to your public key. Okay. Trudy intercepts this message and falsely sends her public key rather than Alice's public key. Then you are basically in trouble because Bob has gotten a wrong public key thinking it's Alice's public key, and you decrypted it and you basically let Trudy. Okay. So the problem with the protocol is that it requires what is called secure key distribution. There has to be a secure way to make your public key available to someone without somebody else going and replacing it. Okay. And as I said, public key you just make public. Okay. People often put it on their web pages. You can go, so several people say, here is my PGP key. It's on their web page. Okay. Now if you actually extract that public key from someone's web page, you better be sure that nobody has hacked into the web page and replaced that public key with something else. Okay. This is exactly that scenario where Trudy has sent a message to Bob saying I'm Alice, and if Bob has to go to Alice's web page to get her public key, okay, and if the web server was actually hacked and that public key was replaced by Trudy with her public key, and Bob is going to extract the wrong public key and mistakenly authenticate Trudy as Alice. Okay. So secure key distribution is an important problem. Okay. The protocol is only as secure as key distribution. Okay. The way to think about this analogy is, let's say you want to guard your home and you buy a big lock. You're saying this is a very secure lock because it's big. Okay. But the lock is only secure if you guard the key. Okay. If you leave the key under the mat before you leave the house and put a big lock on it, that's of no use because the intruder can actually take the key and open a secure lock. The same problem here. Okay. So keys have to be guarded. If you cannot guard the key, the protocol is not going to help you. Okay. All right, so that's this attack. So we talked about. So that's a very quick overview of authentication. Okay, so we'll now use this to do more interesting things that we are actually are more relevant in distributed systems. Okay, so that we needed to have a quick background of encryption, decryption, and keys to do this. Okay. So the first thing we are going to look at is what is called digital signature. Okay. Digital signatures are a way of signing any message or even real documents, and they are supposed to basically be equivalent to actually physical signing of a document. Okay, but you are going to electronically sign a document. Okay, it could be a message, it could be actual contract that you are going to sign with a bank or whatever. Okay, but you want basically a way by which you can use a digital form of a signature. Okay, and we want the following property. Okay, the first two properties. First property is, if you sign a document, the other party has to be able to verify that you signed it. Right? And secondly, if you actually signed it, there should not be a way by which you can claim you did not sign it. There should be a proof saying you signed it. Right? So if you write a check and the bank cashes the check, and if you show up at the bank saying I never signed it, the bank will show your signature. Okay? And say this signature seems to match what we have in the record. Now, unless the adversary is actually a very good forger, typically if the signature is your signature, you cannot say it's not mine. Right? So same thing, if you actually sign it with your digital signature, the other party should be able to prove to you, and you will not be able to say no. That's called repudiation. Okay? You cannot say I never sent that. Okay? How do you do this? Okay? Now, so basically we want the ability for Alice to send a message or a document to Bob which is signed by Alice, and then Bob can verify it's signed, and Alice cannot claim she did not sign it. You want those properties. If you have those two properties, then you have what are basically what you can call as a digital signature. Okay. So here is a very simple form of a digital signature where we are going to use public key cryptography to implement them. Okay. And the idea is very straightforward. Take any document or any message, okay, and you encrypt it with your private key. And basically the process of encrypting your private key is going to be the same as signing that document. Okay. So if you now give this encrypted version of this document or message to Bob, okay, say here is my signature, or here is the signed document. First, Bob can verify that you signed it because Bob has your public key. Bob can actually decrypt it and says yes, it's the same document and it's signed with your private key. So only you could have signed it. So Bob can have some assurance that it's actually signed by Alice. Right? Second, Alice cannot claim that she did not sign it because only she is supposed to have access to her key. Okay? So if you have if you have an actual contract, you cannot never sign that because it's signed with your private key. Okay? So only you are supposed to have signed it. Yeah, unless your private key got compromised, but that's a different problem. Okay? So long as your private key is only yours, you cannot claim you have not signed. So public key cryptography gives us the basis for implementing digital signatures. Okay. Now the claim here is that typically you would not do this because this is too expensive. Typically secure public keys are very long keys. They may be 124, 1024 bits or 2048 bits. So encrypting any large document with that key is a very compute intensive process because encryption is computationally intensive, so is decryption. So if you're taking a 60-page document and trying to sign it, it may take hours for that computation to actually complete. Okay? So you want a more efficient way to sign a document that is less computationally expensive, but just as secure. So there's nothing wrong from a security standpoint. Okay? This is a fine protocol. The problem is its computational efficiency, okay, which is poor because public key cryptography is very secure, but also very expensive to implement. Okay, it takes a lot of effort computational effort to encrypt and decrypt documents. So what we are going to use to implement digital signatures is what are called message digests. Yeah, I don't know if any of you have heard of a digest. A digest is basically a summary. Okay, that's the definition of what a digest is. So you have a document, if you have a digest of it, that's the summary of that document. So we are going to use message digest to implement this, and basically this is the protocol here. Okay. So message digests are essentially hash functions. Okay, this is a simple hash function. So what the hash function does is it takes any arbitrary length string and it hashes it to a fixed length string. Okay, so you may have a 60-page document. You will basically, if you apply this hash function, which is a digest, it is going to give you maybe a fixed length, 512 byte summary of what that document is. Okay, so you are basically going to take an arbitrary length string. It could be a string is a document because it's just a collection of bits. You basically hash and you get a fixed length. Okay? Depending on the hash function, the length of this hash will vary. It could be 256 bits or 512 bits or bytes or whatever it may be. Okay, but it's a fixed length. So you can take arbitrary length document and convert them into a fixed length hash. And the idea is that you will actually sign the hash, not the document itself. Okay. So if you sign this hash, this is significantly smaller than the original message. It is cheaper to sign with your private key than the original document. Okay. So the way you are going to implement digital signature is take a message M. First you generate a hash of that message H of M, and then you are going to basically encrypt that. So then the signed document is the original document unencrypted and an encrypted version of the hash of that message. Okay. So this is basically a signature of this document. Okay. So the claim is this is roughly as good as what we saw on the previous page. First of all, you can use the Alice's private key or rather public key to extract the hash. You can recompute the hash of this and then compare the two, and then you will know whether it was signed or not. Okay, this is how you will verify the signature. If somebody say go verify whether Alice signed this or not, you take the document or the message, compute the hash. The hash function is assumed to be well known. That's not a secret. Only the keys are secret. Okay, so you compute H of M and you go get Alice's public key. Okay, decrypt this message and out comes H of M, and then you compare. If the two match, then you say only you could have signed this because this hash is signed with your key. Now if somebody changes the message or document, you have M prime, that will generate a different hash. Okay, so if because M is not encrypted here, the document is this. If you have a contract and somebody goes and says, rather than you promising to pay $100, if they say now they change that to 200, okay, that's a different document. Okay, when you hash it, it will produce a different key. So you can claim I never signed that because that's producing a different hash. I only signed a document that produced this hash. Okay, so that's all okay. And you can verify that the person has signed it. The person cannot deny signing it so long as the document produces the same hash. So all of this basically works well so long as we have some good properties of the hashing function. Okay. So you basically want the hashing function with some good properties. Okay. First of all, given a hash, okay, given this hash, you shouldn't be able to construct some message that will generate that hash. Otherwise, you will basically be able to construct arbitrary messages and claim that you signed it because I have a signed hash. Okay, so given some digest X, it should not be feasible to find a message Y that will produce that hash. And then I can say basically you just signed something that you never actually signed because I can generate arbitrary fake messages that are producing the same hash. Okay? And second is the probability of collision should be very low. There should be given two messages X and Y. Okay? The probability that they hash to the same value should be small. Okay? Notice that it cannot be zero. Okay? Because the hash function takes arbitrary length strings and maps it into fixed hash of a certain length. So there will be a number of different strings that will produce it because you are basically reducing the number of bits. Okay? So there will be, like in any hashing function, there will be collisions. So that's a given. But the probability of a collision should be very, very small. Maybe if you have these two properties, then this algorithm or technique will work well in practice. Okay, so you shouldn't be able to guess a message that given a hash, guess a message that produces it. And you shouldn't have two messages that produce the same hash because that will also cause a problem. Yeah, the collision should be, probability should be very small. Okay. Any questions here? Okay. So people, I will look at later on in the class where there are emails that you can actually send with signed versions. So you can verify that the email was not changed in transit and so on. This is exactly what's happening. You take the body of the email message, you produce a hash, you sign it with your private key, your public key is known. So you can actually verify that the email is not being modified in transit. So this is actually used in a variety of different contexts, including secure email. So there are many hash functions that are actually used. And there's one called MD5, Message Digest version 5, which is no longer secure. Okay, but it's actually mentioned in the book, so I just put this slide up. So what this does is it basically takes arbitrary messages and generates 128-bit versions of hashes. Okay, there's a long protocol. Okay. It uses a large key and then it uses a set of subsets of those keys and rehashes them a number of times. There are a number of rounds where you take that message, hash, another hash, and so on until you get the digest. No reason to actually go into the details of what the hashing function is, etc. Simply because MD5 is no longer secure. Okay? It's simply 56-bit key hash functions, and today that's just not secure. Okay? So you can actually, some of those properties that I mentioned on the previous slide no longer hold. Okay? So if you actually have any system that uses MD5, I should tell you that that system is not going to be very secure because MD5 is not a good hash function anymore in today's world. So what is used actually are more sophisticated hash functions. There's one called SHA hashing. This is quite popular and used commonly. SHA stands for a secure hash algorithm. It is either uses 160-bit or there are SHA 256 and 512 use basically larger keys to do the hashing. And by basically virtue of using larger keys, you cannot run brute force attacks. The reason you can basically, the small keys lend to brute force attack is you can basically do this. If you have a short key, okay, you can start enumerating every string that is possible. Okay, and then see if that string and then hash that string and see if you will basically get this. The larger the key, the more computationally intense is the hashing and less likely it is that you can launch a brute force attack. That's really the point. Like any encryption scheme, you can also launch brute force attacks on hash functions, and this is why the hash functions are also basically using larger and larger. Okay. Any questions here? So I should mention a word or two about brute force attacks as well. And no matter how secure your function, the encryption function, it is always possible for an adversary to launch a brute force attack to guess the original message. Right? So, if you are basically message saying I am Alice and this is encrypted, okay, the adversary can always capture the encrypted version of the message. Adversary doesn't know what the message is, but adversary can have access to lots of computational resources. Say, you have a large cluster of machines. Then you can simply start enumerating every string that is possible. You just say string A, B, take all the words in the dictionary, start constructing all the sentences you want. And for each sentence, just use the public key to encrypt it or rather decrypt it and see whether you basically get the same message. Right. So you can always launch brute force attacks to figure out. Yes.
I was just going to ask if these SHA hash functions are scalable, in the sense that I can just include more bits in the future when computer resources.
The basic point is, as computers are becoming more powerful, the sizes of bit, the number of bits used to do the encryption or hashing are also growing, just to make sure that it is beyond the reach of today's machines to do the brute force decryption. So that's basically why they're going longer and longer. And the point is, if you have a technique by which you can launch any brute force attack, it's fundamentally insecure. Okay? And people actually think that if quantum cryptography were to actually come into becoming practical, then all these encryption techniques are going to be in trouble. Because all of these are exponential complexity to launch a brute force attack. But with quantum cryptography, you can do exponentially complex functions in linear time. But luckily there's no quantum computer that you can go and buy. But if that were to come to pass, then these techniques will no longer be secure. You'll need to basically come up with other techniques. But for today's machines, these are fine. Okay. 10 years from now, maybe not, because the machines will become more powerful. So you might actually have to basically keep increasing the number of bits or come up with more clever encryption. So there is always this game of cat and mouse as to the encryption algorithms have to stay one step ahead of what is possible by today's computational resources. Okay. Okay. So now I mentioned this notion of all of the encryption algorithms are only as secure as key distribution. If your key cannot be distributed in a secure way to the other party, and some intruder is able to grab your key, then using that encryption is not going to work. If your key is known, then the encryption, however secure, is not going to buy you much. Okay? So we need to be able to essentially have a way by which you can generate these keys in a secure way. And there are multiple techniques to do this. I'm going to show you two. Okay. One technique uses a trusted third party. Okay. Often in many encryption or security algorithms, there's a trusted third party, and that third party is what you go to figure out whether something should be done or how to do it. So the first protocol here is going to use this notion of a secure third party, which is a key distribution center. So you can the assumption is you can trust that entity but no one else. Okay. So now the problem is very straightforward. Alice and Bob want to communicate securely, and they want a one-time symmetric key. Okay. They want to generate this key and have it be distributed to both of them in a secure way. Okay. So basically this is the way it will work. Alice will send a message to the key distribution center, that's a machine, a trusted machine, saying, I'm Alice, I want to communicate with Bob, generate a key for us. Okay. So what the key distribution center will do is it will generate a key. Okay. It will encrypt that key with its private key, okay, and send it back to Alice. And the assumption is that the key distribution center, since it's a trusted machine, its public key is well known. Okay, so this is the private key. When this public key is known, so you will basically be able to extract that key out from the key distribution center. So message and then communicate. Same message is sent to Bob. This is a special key that is being generated for communication between Alice and Bob. So you can ask the question saying, if I think recursively, how do I know that I can get the key distribution center's key securely? Okay, because we are trying to say, get me a key for Alice and Bob to communicate. Okay, and the key distribution center gave me a key, but it was encrypted with the KDC's key. Okay, and the assumption was you knew the KDC's key. So where did you get that from? Right, so you basically can have this recursive problem. So the assumption, we basically have to sort of have this level of trust where we assume that the KDC's key is known. It either comes pre-installed on your machine, okay, or is widely published. Okay, you take an ad in a newspaper. So this is it. Right? So I mean, basically you have some way of distributing it widely so that everybody is assumed to know it. So there is no need to distribute it. Okay, so it's sort of public knowledge. So you don't have to actually distribute it. So then once you know that, then you can generate a key that two parties need to use. Yes.
So why can't a malicious user use the key that is coming back from the KDC to Alice and then use that to impersonate Alice to communicate with Bob? So KDC is generating a key and sending it back to Alice. Someone
Yes.
could just sniff that packet, use the KDC's public key to decrypt it and
Right. So here is a key that, so in this case I should have rephrased what I just said. This key is basically a key. Here we are at the next slide. I'm going to show public key cryptography. Here we are not using public key cryptography. We are using a key that Alice and KDC know. It's a secret key. This is a key that is only known between these two parties. Here is a key that's only known between these two parties. Just to answer your question, here is the KDC protocol that is going to use public key cryptography. Right? So one more slide. Here, this one. This is public key exchange. This one is actually going to use a nonce. Okay, so this actually doesn't even need trusted third party. You are going to just say, I'm Alice. Here's a nonce. I've encrypted this with my private key and send it over to Bob. Bob is going to decrypt it with Alice's public key. That's known. Okay, and generate own nonce. So I decrypt that saying, here is your nonce. Here is my nonce. Reverse challenge. Here's a key I generated. Okay, you send it back. And then Alice sends back an acknowledgement saying, okay, I did get your nonce, here it is back, and I'm encrypted with your key. Okay. So you can essentially do that. there's one more protocol here, which basically says how do you get the key of the trusted server. Okay, so this is basically the question you were asking, right? So what this allows you to do is essentially extract Bob's public key from a trusted server. Okay, so you basically send a message to the server saying, get me Bob's key. Okay. The server is going to essentially send that Bob's key but encrypted with Alice's key. Okay. So if you sniff this packet, you will not be able to extract anything because you don't know, only Alice knows his private key. Okay. So the basic answer to your question, I'm going to back up a little bit. The basic answer to your question is, when the key distribution center sends something, it has to be encrypted with Alice's key. Since that key is well known, okay, you cannot sniff this packet. Okay. Does that answer your question? Yes. Any other questions here? I hope people got the gist of what the question was. Would you basically, if the KDC simply encrypted this message with its private key, since its public key is well known, this message can be decrypted by anyone. Right? What I was pointing out is basically you wouldn't do that. What you would do is you would encrypt it with Alice's public key, not with your own. And you may sign the message using your private key. In that case, you cannot actually fill it. Only Alice can decrypt that message. This is why it says it's encrypted with a key that only Alice knows. Okay, which is basically you can encrypt it with a public key. Okay, so there are more complicated versions of the protocol here that I'm going to just ignore. Okay, the basic point is you can either use key distribution center or you can direct do mutual authentication using private and public keys and nonces. Okay. Now all these protocols, although we are sort of seeing just random messages, they're actually implemented in distributed systems. Whether you use Kerberos or you use SSH, these are some of this is the basis of what is actually going on underneath. Okay? Even I'll show in a little bit, the process of even setting up an SSL connection between a web browser and a web server involves some of these message exchanges. It uses public key cryptography. It also uses this notion of a digital certificate, which I'll show you as well. Okay, so any questions on this before I talk a little? So I wanted to present that material and then say a few things about firewalls and actual systems that are used, not protocols. Everything I talked about until now has been protocols and encryption and decryption. Now we'll actually look at systems and how they use many of these ideas. Yes.
Back up a little bit. So what is the fundamental flaw in using nonces? I mean, what is the fundamental attack mode that you can use?
For nonces?
Yeah, as with the initial protocol, I think AP4 or something that you described.
This one?
The one before this.
This one there is no.
No, AP4.
AP4. Okay.
Yeah. So what exactly is the problem with nonces that you mentioned in this slide?
There is no problem with the nonce so long as you cannot regenerate the nonce in the lifetime of the application.
Okay. And we also assume that both A and B must have a common key amongst each other.
Correct. So basically the only issue here is there's no problem with the nonce. If the key is compromised and the algorithm is compromised. That's all that there is a problem. So long as the key is shared in a secure way, there is no such problem here. Okay. Now the issue with public keys is that public key has to be given out in a secure way. Okay. If you ask me, give me your key, and you send me the key in a way that can be compromised and somebody else can substitute their key, I have somebody else's key thinking it's your key. That's the only problem. Otherwise, there is no problem with any of these protocols. The issue is key distribution. Key has to be distributed securely. If that's the case, then there is no issue. Okay. So, how do some of these ideas get put into practice? So, if you actually look at many systems, there will be encryption to do authentication. There is going to be use of message digest and signing and so on. But there's also authorization. Authorization is the problem of ensuring that only the right set of people or machines get access to the right resources. So you will have typically on a machine you will have administrator level privileges and user level privileges. Users have a more restricted set of privileges of what they can and cannot do, but administrators have nothing. There are two binary models. So restricted user and sort of full you control. But you can have anything in between where you can say this user can do this other user can do this administrator can do whatever they want. There are many ways to specify these rules of who can access what. The simplest way, this is all comes under this notion of access control. The simplest way is basically referred to as access control list or ACLs. In an access control list with every resource, there's a list of users that basically tell who is authorized to access those resources. Simplest way to think about this is files. For every file on your system, you have a list of who can read, write, or execute that file. In Windows, you can actually construct a list. In Unix, basically there's a course list used that is owner, group, and world. But there are modern Unix systems that also allow you to attach a list. You can say this user can read, write, execute, this user can only read. So whenever a user, after authentication, user wants to perform a certain operation, that operation has to be checked against the access control list. Right? And only if that user has the right privileges will you allow that operation to proceed. Okay. So one way to basically decide who gets to do what is to essentially have access control lists that are attached to resources. Okay. Another way to specify this, and this is the ACLs are actually the more common way, but another way to specify this is this notion of capabilities. Okay. So think of capabilities are attached to users, access control lists are attached to resources. Okay. So if you have a system that uses capabilities rather than access control lists, what happens is every user or every entity, a program let's say, is basically given a list of capability. These are the things it can do. Okay? So when it tries to perform an operation, it presents a capability to the system saying, look, I have the right to do this. Okay? And then you basically check, does this person have the right to do this or not? Okay? And then you basically let them do it. So there are two different ways of doing the same thing. Achieving the same thing. So essentially, you have users and you have resources. Okay. If you basically maintain the list, attach a list to every resource, you basically get access control list. And basically for each resource, you basically have a list of users and operations that they're allowed to do. And you attach it to the resource. If you do this, you have a system that does access control. Okay, that's what you see. Another way to do the same thing is, and then users just come in and you just check whether they are in the list or not. If you have capabilities, you basically have users, and here you have a list of resources you can access. So this is what you attach to users. So when users come in, you basically and try to access resource A, you see is resource A in your list or not? Do you have authority to access? Okay. So if you do this, you have a system that is basically capability based. It's exactly the same thing whether you do it, attach the list of rules to resources or users. This question.
To be secure, though, you wouldn't actually want the client to pass the capability, though, right? Because they could just pass whatever they want.
So question is, to be secure, you don't want clients to actually pass the capabilities because they can pass whatever they want. Typically, clients won't pass it, but the system, the OS, will maintain the rules against users. Okay, so this is assumed to be actually done in the user and OS. So the question is the OS going to keep for every user the list of resources he or she can access, or for every resource the list of users that can access the resource? Depending on the two, you have these two things. Okay, so and most systems actually do this. This is what we are used to. There are some systems that also do capability. So you will actually see occasionally systems that use capabilities instead. Okay. So that is how you typically do access control. Now we'll try to put all of these things together in the context of enterprises and so on. So now When you go to any enterprise, whether it's a university or a company, and ask maybe the network administrator, what do you use for security and whatnot, there will not be one answer, okay? Because typically most organizations will have to use a set of different techniques in order to have a secure environment. Okay, so this is a multi-layered approach. So you will have one or more, all of this. You may have firewalls. Firewalls will guard what network packets can enter and leave the enterprise. Okay. You may have systems that do what are called deep packet inspection. Okay. These are systems that not only look at source and destination address from where the packet came, but they actually look inside the packet. So is there something bad in the packet? You can actually virus scan packets before letting them in, for instance. Okay, so you actually have systems that look inside packets to decide whether to let a packet in or not. You of course have scanners to that scan files or scanners to actually check the email as it comes in to see if the attachment has a virus. So there are all these scanners. There are virtual LANs or VLANs as they are called, also configured. So think of a VLAN as a virtual network such that packets from one virtual network cannot actually access machines that are another virtual network. So rather than putting all the machines on a single Ethernet, you take the machines and you put them on logical Ethernets, your logical LANs. Okay, this creates a separation between machines. So even though another machine may be on the same network, if you are on a separate LAN, you cannot actually access the machine because the switches will prevent your packets from reaching that machine in the first place. Okay. So you can physically separate machines out. Okay. You can use radius servers, so these are password databases. You can use secure versions of Wi-Fi. You can use virtual private networks to allow access from outside. And you will use a variety of services that run on SSL and certificates and so on. Okay. So I will not go into all of these bullets. I just want to mention this to you so you can understand that the task of keeping any enterprise or any network secure is very complex. Okay. There are all these different things that are put in place. They all have to be configured. Most of the time, the environment is so complex that if you misconfigure something, it allows the hacker to actually get it. And this is how a lot of intrusions actually occur. Okay. So it's one thing to say I have a secure encryption algorithm or I have a secure message digest technique and so on. But it's another thing to actually put all of these techniques into practice. Okay. And the same would be true if you have a distributed application. Okay. So if you have any multi-tier application or any distributed application, there will be databases. Databases have their own passwords. There will be web servers. Web servers will be communicating over databases. RPC messages are actually going from one machine to another. Should they be encrypted? Should they not be encrypted? What if some adversary could sniff those packets? As packets coming from outside, clients are accessing your system. Okay, which packet should you let in, which ones not to let in? So there are all these complex policies you have to actually put in place as to how to secure your application, okay, and how to encrypt all the communication and so on. So it's a fairly complicated task to implement security in most of these services. Okay, so I just talked about internet services. So same thing is true. If you have any internet service, you have to do all of these things. Okay, you have a website maybe. Okay, that website, if you want it to be secure, has to run over SSL. This ensures that all packets going from the browser to the web server is encrypted. Okay. You have to use authentication. Okay. You have to ensure that users actually log in before they are given access to your system. Okay. Without logging in, you will not allow access to certain things. Okay. You will use things like captchas to prevent people from creating fake user accounts and all this kind of stuff. Okay. I don't know if people have probably heard of captcha, right? You go create a new account on a website. It shows you some text and says type out that text. Okay. The assumption is that it's easy for a human to figure out what the text is, but not a program. Okay. Because there are scammers who just write programs that go create fake accounts and cause problems. So all these issues you have to actually deal with. And you may have to do challenge response authentication, which is more secure than simple password-based authentication. Okay. So in Gmail-based services, for instance, this is also referred as two-factor authentication. So it is no longer considered secure enough to have a username and password, where somebody can guess your password. Most people are not good at having secure passwords. That they use dictionary words and whatnot, so that lends itself to brute force attacks. Okay. But if you have two things, not one, then it is actually much more secure. So what is typically done is you try to log in. If you do two-factor authentication, when you try to log into a system, you specify your username and password. Okay. And then a once in a lifetime challenge is sent to a device you're supposed to have. In this case, a text message may show up on your phone saying, enter this code. Okay. So in addition to the password, you'll have to enter the code. And the assumption is that even if your password is compromised, maybe you have your phone, or if you lose your phone, maybe you didn't put your passwords on the phone and encrypt it. So let's assume. So you have to have both. Okay, so the probability that both are compromised at the same time is much lower. Okay. These are more complicated forms of authentication that will come once more and more services start to implement. Okay, some services are already doing. Okay, you can actually go to systems like Gmail, and even Amazon is starting to do this and say, I want two-factor authentication. Then you will need a password and a device. Okay, the password, you know, the device will give you once in a lifetime integers or codes that you are actually going to enter. Okay. There are others that allow you to do one-time passwords, like Nonces. Microsoft has implemented this one-time password for Hotmail, for instance. Okay. And then there are many other things that we'll talk about payment systems in a little bit, that you have to deal with all sorts of other forms of authentication and so on. Okay. So this is just a flavor of things. I mean, clearly we do not have the time to go into these things in detail. So it requires several lectures worth of material. But just to give you a flavor of security in distributed system is complicated. And there are all these things to be aware of, all the things to be actually dealt with in order to make things secure. Any questions on this? I'll just show a picture of what a firewall does, just so that you get a sense of how firewalls work. Okay. If you're more interested in this kind of stuff, there's networking courses that go into this in more detail. But here's basically a picture of a firewall. Okay. So what happens in a firewall is, think of it as a network device where there are packets coming from outside the device and packets coming from inside the network. Okay. So what is on this side is basically your secure network. What's outside is everything outside. So this would be the internet, that's the rest of your environment. So if you have a firewall sitting on the UMass network, for instance, the inside is all machines within the UMass campus. Outside is all machines outside the UMass campus. Okay. What a firewall simply does is it examines every packet that is going in or going out. Okay, and it compares that to a rule that the administrator has specified. Okay, the rule says what is allowed and what is not allowed. Okay, as simple as that. So you can basically have any rule can be specified. Okay. The rule has to say basically source address. Okay, so a simple rule might look like source IP, port number, destination IP, port number, and then you can say allow or deny. Okay. So you can specify a rule. So you can say all port 80 traffic from outside must be blocked. Okay. So you basically have a rule that says you put a wildcard saying any IP address sending traffic to port 80 to machine inside is basically denied. So what this will do if you put a rule like this, anybody from outside UMass that tries to access a web server that's inside UMass will not be able to access it. So you basically, any packet that's going to port 80, you will match that rule and drop that packet if such a packet comes. Okay. So you can say block services, you can allow services, you can configure these rules in arbitrary ways. Okay. So you could say, like there are organizations that say, when you are like banks and other financial organizations, that for security reasons do not allow you access to outside services. Like say you cannot access Gmail while you are at work. Okay, so you can specify some IP addresses and say from when a packet tries to goes out, if it matches with IP address, drop it. So then you can actually deny access to outside services, for instance. Okay, so you can implement whatever policies you want. Essentially what's happening here is you are doing packet filtering based on a set of rules. Okay, the rules tell you whether the packet should go ahead or not go ahead. Okay, so that's basically how any firewall works. Now, who makes these rules? That's up to the network administrator. The network administrator is implementing whatever policy that organization wishes to implement. Okay. So these are simple packet-based firewall. There are other things that you can do which allow you to actually scan a packet and decide whether to allow it or not based on the contents of it. Okay, so you can actually look for virus signatures in packets as they are going through. And if you actually start seeing any virus signature, you can dynamically block all traffic from that machine, saying this machine is trying to send content that has virus in it. Those are more complicated. Those are not simple firewalls. Those are machines that do what is called deep packet inspection. They're actually looking at the contents of the packet, not just which machine sent it or what port was it sent to. That requires more computational horsepower as well. If you have to actually look inside a packet and do arbitrary things, you will not be able to do them with simple firewalls or gateways. Okay, so those are application gateways. So one last point I wanted to sort of make here before talking a little bit about payments was this notion of secure email. Okay, just to give you some flavor of how can you make email more secure. Typically, any email messages that you send are sent unencrypted. Okay, so any intruder can see your message, okay, and anybody can alter that message. And the other party will not know whether the message was altered in transit or not. Okay. So if you need basically to send secure email, you will need to do two things. One is you will need to encrypt the message, and you will need to sign the message. And then if you do both, then you are basically going to get a secure. So these are the requirements that we will impose to have secure email. First, you want secrecy, that nobody else can see what's in the message. Only the sender and the recipient can actually see the contents, but no one else. Okay? That's the secrecy property. Okay, sender authentication. How do I know that the message came from you, not some spammer? Okay, typically, you get some garbage messages from spammer, and they can stick whatever from address they want and make it look like the message came from someone else. Okay, that's trivial to do. Okay, so when a message comes, typically you cannot actually trust that it came from who it says it came from. Okay, because email doesn't guarantee you any authentication. So how can you add sender authentication to the protocol? Okay. How can you ensure message integrity, which means that it has actually not been altered in transit? Nobody has gone and modified the message. Okay. And can you also do receiver authentication, that only this person can actually see the message? So some of these things you can simply use public keys. Okay. So you can say, I want to send a message to user, Alice wants to send a message to Bob. Okay, Alice is going to take Bob's public key, encrypt her message and send it off. Okay, and only Bob will be able to decrypt that message. So secrecy is actually going to be guaranteed with that. Okay. I already mentioned that that's inefficient for long messages. So what we can do is we can actually use slightly more efficient protocol to achieve the same result. So here is what we can do. Alice wants to send an email to Bob. Alice generates a symmetric key of her choosing. Okay. Alice will then encrypt that email message with that symmetric key. Okay. Because Alice generated the symmetric key, the key is not known to Bob. The key will also have to be sent to Bob. Okay. So what we will do is we will take the key and we'll encrypt it with Bob's public key, which is known to Alice. Okay. And the email will actually contain these two parts. Okay. It will have the encrypted form of the message, which is encrypted with the key K. This is the message M. Okay. And the key itself is encrypted with Bob's public key. Okay. And you send these two things. So only Bob can extract this key, because the private key is only known to Bob. Nobody else can actually get the key. This is an encrypted form of the message. So this message is pretty much useless to anyone who doesn't know the key. Okay. So Bob can use his private key to extract this key K. And then once you know the key K, you can decrypt the message and decrypt the email. Okay. So this is a way by which you can send secure email. So you'll get a secure email and only you will be able to read it. But this protocol, as you can imagine, by itself doesn't tell you that Alice sent the message. There's nothing here. Anybody can generate, Trudy can generate a message M and send it off with Alice's from email address. Message will appear saying from Alice and it will have this. Only Bob will be able to read it, but Bob cannot actually get any guarantees that actually Alice sent it. Okay? The reason is Alice has not signed the message. He only encrypted the message and sent it off. If you want to guarantee to Bob that only you sent it, you also have to sign it in addition to encrypting it. Okay, clear? So here's so we'll now see how to do signing. There's no encryption. Signing is very straightforward. We are going to take a hash function h. We will apply the hash function to the message, okay? And we'll basically have Alice sign the hash. This is a digital signature of the message. Okay? So then Alice is going to send a message M, okay, and send the hash which is signed with her private key. Okay? So Bob can now verify that Alice sent the message by taking the message contents, hashing it, and using Alice's and extracting this hash from this encrypted form of the message, because Alice's public key is known. Okay. So if you use this protocol, this is using digital signing, but it's not using encryption. The message is going unencrypted. Okay. The previous part told us how to encrypt the message. This part is telling us how to sign the message. Okay. So you have to put the two together to actually generate a secure email protocol. So this is how it's going to work. You are going to first generate a hash, sign the hash, okay? And then basically you have the message and the hash. You will also generate a key, okay, that you are going to use to encrypt the message. Okay? That's M prime, you encrypt M prime here. Okay, and then you are going to send the key itself encrypted. So what you are going to send is K of M prime and the key encrypted with box public. So you're taking this part and the other part and you're putting the two together. Okay, so you have a sign, you sign the message, you encrypt the message, okay, and you send the encryption key using Bob's public key, so only Bob can extract. Okay. So if you actually have any email client that allow you to send secure email, this is what it is doing. Okay. Many clients actually allow you to configure the client to actually send, so whether it's Thunderbird or Apple Mail or whatever, you can actually install a key and it will allow you to do this and send encrypted messages to some other party. Okay, so this is how, and you can also use PGP to do the same thing. PGP is an open protocol that allows you to generate keys and so on. You use PGP keys to send encrypted messages. Okay, so very quickly I'm going to talk about SSL. So I'll show you how SSL is. You probably know what SSL is if you are connected to any web server where it says HTTPS. Okay, so it's running HTTP over secure sockets. Okay, what secure sockets do is it's same as socket communication, but any packet that you send over a secure socket is automatically encrypted. The application doesn't have to encrypt it. The secure sockets library will encrypt it for you and it will decrypt it at the other end. So a simple way for two parties to communicate and ensure it's secure is to, rather than sending it over a normal socket, you send it over a secure socket. By definition, anything you put into the socket goes encrypted. Okay. And this is basically the protocol that is actually used to do this. So the browser will connect to the server and say, I want to set up an SSL connection. The server will basically say, yes, I support SSL. Okay. And essentially, what the browser will do is it will generate a session key, a one-time session key. It will encrypt it with the server's public key, okay, and send it off. Okay, and then say that future messages will be encrypted and basically send the key or some other nonce. And the server will also say that the future message is encrypted. Now to do this, you need the ability to basically get the server's public key. Okay, so the idea is if you want to set up a connection to the server, to get the server's public key, you choose an encryption key and you send it off to the server saying this is the key we are going to use. So, but the question really is how are you going to get a server's public key? Browsers can't store a list of every server's public key a priori. Okay. So only thing is you are going to have to ask the server to send its public key. Okay. That is this step where you ask the server, and the server essentially sends you a certificate, which includes your public key. Okay. So now you can ask the question, why is that not vulnerable to man-in-the-middle attack, where you try to connect, let's say, to CNN, and you get a public key from a machine that claims to be CNN. How do I know that's that machine but not some other machine that sent me their public key or their certificate? Okay. So the reason this is called a certificate rather than a public key is the assumption that we'll use a third party to verify that the public key that's coming from the server is its own key. Okay. So what happens typically is the server will generate a public key and you'll get a trusted third party to sign it, saying sign this key. Okay, this is called a certification authority. So you now not have a public key, but you have a certificate. Okay, the certificate is your public key signed by a trusted third party. Okay. And browsers come pre-installed with the certification authority's private key. So the browser can actually verify that this public key actually belongs to the server because some third party that the browser trusts has signed it. So if you actually go into any browser, whether it's Firefox or Chrome or Safari or Internet Explorer, and go into the options or preferences and go into security, you'll see a list of certification authorities that are pre-installed. Any key that is signed by those certification authority, the browser will trust. If CNN presents a certificate signed by VeriSign saying, yes, this machine is CNN, your browser will trust that any machine that presents that certificate is guaranteed to be CNN. Okay? So use a third-party trust to make this happen. Okay? So this is essentially what is underneath SSL. You are going to use a trusted third party. You are going to use a certificate signed by the trusted third party, and you will generate a session key to do all of this. Okay? So we are out of time. There's only one small topic left, which is electronic cash and cash payments. I'm going to just defer that to the next class, which is the last class. So we'll stop here for today and continue this next.